So I wanted to continue our discussion about sig figs and specifically focus a little bit on the zeros and when zeros are significant and not significant, and then transition into a little bit of talk about scientific notation and why we would use it. If we get through that, then we'll talk about calculations. If we get through that, we'll talk a little bit about uncertainties in these calculations. So this is kind of, we talked about the rules, and you have the rules on your sheet. This is just a different way of talking about it. Again, I will post these slides. You don't have to take pictures or anything. If you have trailing zeros at the end, and there's no decimal point, we assume that they are not significant, okay? So 210 with no decimal point has 2 sig figs. The 0 is not significant, okay? If, however, we have a decimal point and we have zeros after the decimal point, trailing zeros, they are always significant because those are telling us something about the precision of our measurement, okay? Anytime we have zeros in between 2 significant digits, those are also significant. So 101, the 0 in the middle, is significant. This is true, including a situation where you have a 0 at the end in the ones place, and then you have 1 or more zeros after the decimal place. In that case, all of the zeros are significant, including the one before the decimal place, okay? If we have leading zeros, which we're only going to have if there's a decimal place, right? Because you don't write 0 to 1 0 for 210. Leading zeros are not significant. So if they come before the first non-zero digit, they are not significant. Doesn't matter how many places there are after the decimal point. For example, 0.00681, none of these zeros are significant. They are important. You can't just get rid of them because they're placeholders, but they're not considered significant digits. Now, if you have leading zeros and trailing zeros in a decimal place, again, the trailing will be significant, the leading will not. Okay? So this leads us to a conundrum that your worksheet solves in a particular way that I don't like, which is, what do we do about ambiguous trailing zeros when we have a number like 3,400? Okay? So just looking at this number without any other information, this could be at least 5 different numbers, okay? It could be anything from 3,400 to 3,449 rounded to 2 sig figs, because you would round the third place down and get 3,400. It could be 3,350 and above, rounded up to 2 sig figs, to 3,400. So you have this huge, difference there. It's really hard to say how precise this is. If it was rounded to 3 sig figs, it could be 3,404 or 3,395. Okay, and we don't know that from just looking at this number. It could be 3,400 exactly with 4 sig figs. Now your paper says, God, I hope this works, that you can just put a decimal place there without any trailing zeros, and that makes it 4 sig figs. I don't like that. Nobody in the real world uses that as a annotation, okay? So don't do that. So how could we differentiate between these different possibilities? The answer is not do this, but instead use scientific notation, all right? And I just want to reiterate that if you have no other information and it's in decimal notation like this without the period, okay, you assume that those trailing zeros are not significant. And you're assuming that this is 3,400, but with only 2 sig figs, okay? How can we differentiate between these? We use scientific notation. What is scientific notation? It's a way that we express really small or really big numbers in a more compact form. It's also a way that we can deal with this trailing zero problem. Okay? So, typical scientific notation, you start with a coefficient, you multiply it by your base, which is always 10, unless you're doing something really weird, which you will never do in this class. And then you have an exponent. So what we're doing is we're always going to have a coefficient with one number before the decimal point, just one. Okay? And then we're using the 10 to the whatever exponent to tell us where the decimal place really goes. All right, so if I have 4.5 times 10 to the 6, that's telling me that I take the decimal place and I move it. So this is a better example down here. That's why I put it down here. 4.5 times 10 to the third. I'm taking that decimal place. It's a positive number, so it's going to be a big number. Okay, positive exponent means a big number. And I'm going to move that decimal place 3 places to the right. And I'm going to end up with 4,500. Okay? So positive integer is a big number. A negative integer is going to be a very small number, or represent a very small number. So even though I still have one digit before the decimal place, the fact that my exponent is negative means that I'm moving this decimal place to the left to make a smaller number. So 6.77 times 10 to the negative 2, I move that decimal place twice. I put zeros in wherever I don't have a placeholder, and now it's 0.0677. Okay? I wanted to bring that up because you have in that practice some numbers in scientific notation. Wanted to make sure you guys were okay working with it. What is a great number in chemistry for which we always use scientific notation because it would take about a year to write it on the board? Yes? The mole, Avogadro's number, 6.02 times 10 to the 23rd. Right? That's 602 with 21 zeros after it. We're not going to write that every time we do a calculation, okay? So that is one situation where you will always be doing calculations in scientific notation. But it's also convenient for shrinking a number that either has a lot of zeros in front of it or a lot of zeros after it, and also for dealing with this ambiguous zero, trailing zero problem. Because if this is 4.5 times 10 to the third, that's telling us that there are only 2 significant digits in that 4,500. If we wanted to look at this 3,400 and look at different ways that we could write this in scientific notation, if it was 3,449 rounded down to 2 sig figs, then it would just be 3.4 times 10 to the third, right? Or if it was 3,350 or above rounded up to 2 sig figs, that would also be 3.4 times 10 to the third. Now, what if we wanted to indicate that we were rounding it to 3 sig figs? But the rounding gets us to a 0. So 3,404, I'm rounding to the third digit. That gives me 3,400. But I can write it as 3.40 times 10 to the third. And that gives me that information, that I have that much precision in that measurement, in that number. Same thing for if we're rounding up to 3 sig figs. Okay? So because trailing zeros after the decimal place are significant, this is how we handle this quandary. All right? If I actually do have 3,400 exactly, but I only have 4 sig figs and I can't stick a decimal point in there, I can write it in scientific notation and show that I have 4 total sig figs. Okay? So that's one of the helpful uses of scientific notation. I will later give you guys a practice sheet about converting back and forth from scientific notation to decimal notation, just to make sure everyone's on board with that. We won't use it a lot, but we will use it sometimes. Okay. So let's just walk through the answers to these problems. So Sylvie, what's the answer to number 1? How many sig figs? Okay, 2. Oops, sorry, gotta go back to my pencil. All right, Valerie, what about number 2? Yep. Jocelyn, what about number 3? 3, because that leading 0 doesn't count. Olivia, how about number 4? Yep. Julia, what about number 5? Okay. What are you thinking about when you look at it? What are some of your options? What's that? The first digit, so maybe just the 3? Okay, so it could be 4, right? Because we've got 4 numbers here, right? These are trailing zeros. There's no decimal point here. Do we count them? No. So how many total sig figs are there in this as written? 2, exactly. Yep. Now, this is number 6, I don't like, but we'll go with the way they talk about it because you might see this on a worksheet somewhere. Sadie, what would you say for number 6? 3, because there is a decimal point there, but please don't do that yourself. When you are writing something in significant digits, please don't put the decimal point without anything after. Put it in scientific notation. All right, Nathan, how about number 7? 3. Okay, so you're saying that this trailing 0 is not significant because it's a trailing 0? Okay. Is it after a decimal place? Does that change anything? Yes. Okay, so how many do we have here? 4. Yep. Okay. Alyssa, how about number 8? 3, because these are all leading zeros before the first non-zero number. Those are never significant. Question? No? Okay. All right. Emmanuel, how about number 9? 3, good. Alexander, how about number 10? Yep. So in scientific notation, only the coefficient, you're only looking at the coefficient for your sig figs. You're not looking at the exponent. That just tells you what the place value is. Okay, so only the things before the x. But anything in scientific notation, everything before the times 10 is significant because of the way it's written. Okay, so Camilla, how about number 11? Good. And Adonius, how about number 12? 5, yes. All of these zeros are after the decimal place, so they are, in fact, all significant. Okay? Any questions about these? Yes?
With 9, why isn't it? Oh, wait, never mind.
Okay. Yeah, if it was just 10, it would be 1 sig fig. But it's because it's 10.0, that trailing 0 after the decimal place makes this significant. And once we have a 0 between 2 significant digits, that 0 also becomes significant. Good question. Anything else? All right. So now that you know how to identify sig figs, I can't remember. Can I see this for a second? I don't think they have. Yeah, there's no practice in this for writing things or rounding something to the correct number of sig figs. I'll give you that in a later worksheet that will also get you practice on the scientific notation. And Olivia, I'll put that in Cami so you can do it online. Okay. So what about when we do calculations? Because it's rare that we just take a measurement and then don't do anything with it. Right? Most of the time in chemistry, we want to know, like, what is the change in temperature in a reaction or something along those lines. So we need to be able to add, subtract, multiply, and divide with these numbers and figure out what do we do with the sig figs. The key here that's talked about in this paragraph up at the top is that you cannot have an answer to your calculation that is more precise than your least precise measurement. If you have a very imprecise measurement, you can't calculate with that and make it more precise. It wasn't that precise in the first place. You can't give it more precision just by multiplying or dividing it by something else. Okay? So, there's two different rules for multiplication and division, addition and subtraction. Okay? When you are multiplying and dividing, it's the least number of significant figures, regardless of where the decimal place is. So whichever number that's going into the calculation has the smallest number of sig figs, that's how many sig figs you get in your answer. Okay? So the example they give you is 2.5 times 3.42. 2.5 only has 2 sig figs. 3.42 has 3. I cannot do this calculation and somehow give this number an extra sig fig just by doing the math. That doesn't work. So my answer can only have 2 significant digits. So you do the calculation, you plug it into your calculator, and your calculator says 8.55. And you say, but I don't have that last 5. That's not a real number. Okay? That's just an artifact of the calculation. So you got to round that to the smallest number of sig figs. So you're going to round 8.55 to 8.6. Does that make sense? Okay. So multiplication and division, find the lowest number of sig figs and go ahead and write it on top of the numbers that are going into it if it helps you. And then do the calculation. And then when you get your answer, you don't have to, if you're doing multiple steps, you don't necessarily have to round each time. You can just say, my final answer can only have X number of sig figs. Okay? For addition and subtraction, this is different. It's not the total number of sig figs that we care about. It's where is the decimal point. So you're going to line up the decimal points on your numbers and figure out how many decimal places do you have. Okay? So I didn't, let me borrow yours for a second. Oh, they don't give, well, they give a couple practice problems, but let's just do this. 23.1 plus 4.77. I'm not going to go beyond that, but you can look at that if you want. 0.1 plus 4.77, okay? Both of these have 3 sig figs. So you might say, well, my answer should have 3 sig figs. That's the rule for multiplication. That's not the rule for addition and subtraction. What we have to do is put our, line up our decimal points, okay? And you can see that there's nothing here, okay? There's no number here. So our answer can only have 1 decimal place. Okay, so I'm going to do this, and I'm going to say, okay, this is going to be 7.872. Okay, so my answer and the calculator, and if I'm doing it in my head, is 27.87. I don't have 2 decimal points, or 2 decimal places. So I would have to round this to 27.9. Okay? So addition and subtraction, you have to line up the decimal points. And the smallest number of places is going to be the number of decimal places, number of places after the decimal that you get to keep. There are reasons for this. I don't know the details of the math well enough to explain them, but just there's 2 rules, follow the 2 different rules. Just a reminder, we're just going to use regular rounding here. There's other methods of rounding if you're going into engineering that try to avoid bias. We're not going to do any of that. We're just going to find the place that you're rounding to. Look next door. Look at the place after that. If it's 5 or greater, add 1 to your place. If not, just drop everything off. Okay? So 54 goes to 50, 55 goes to 60, and so on. I know most of you have been doing this forever, but some folks never picked this up in earlier math classes and need a reminder. Any questions on this? Okay, so you have a bunch of practice problems, adding and subtracting, and I would just go ahead and write in your picture, or on your sheet, line up decimals, or smallest decimals. That's what your answer is going to be. Sorry. And then multiplying and dividing is just smallest number of sig figs. Okay? Let's go ahead and take the next 10 minutes to work on this. We'll go over a few of them together at the end of class, and I'll introduce uncertainties tomorrow. That'll make things a little easier, a little more separation for you.